put this in here. Okay, I'm just gonna crack it. Well, welcome. Welcome to our third lecture now, right? Oops, well, hopefully no one tries to come in now. Welcome to our third lecture. We're going to pick up where we last left off, as I stated off the record and now on the record. We're kind of prefacing this semester by actually running through a slide deck on the primer material that covers the Essential C document and the Unix Toolbox document. And I think both those kind of rally in a very productive way towards going into the first chapter, which kind of gives you this overall tour of what's going to happen from the moment you go ahead and author a source code file until you actually execute it. And of course, the remaining portions of the semester from here until the end is really to take a deeper dive from that very brief topical journey we'll be taking in the first chapter. Now, I already queried the in-person class. I'll go ahead and query the online class as well. Has everyone had the opportunity to kind of fulfill the first homework, which is to read the primer materials for which we're actually lecturing on right now? And so that should be the Essential C PDF, which you should find in the syllabus on Canvas. And it should also be the Unix Toolbox guide, which is also a PDF available on, or at least a link to it on the syllabus on Canvas. Then after that, we'll pivot to the textbook and we'll remain on the textbook for the remainder of this class. Okay, so with that said, does anyone have any questions before we pick up where we last left off? Where we last left off, we had worked our way through section 1 of the Essential C document. And as we first saw when we examined the slide deck at the PDF itself, I want to say it has an introductory section and then it's 7 numerical sections, 7 numbered sections. But the last section, if I recall correctly, is more like an appendix section of sorts, right? Okay, so fortunate for me, all of you have had multiple semesters of programming. So let's see if we can't work our way through the rest of this with the assumption everyone's read the content now pretty briefly. So the first thing we're going to look at now is going to be section 2, which is going to be our control structures. You're going to notice that a lot of the control structures that you've experienced in Java, again, very heavily inspired as being part of the C family, this is the genesis. So when we talk about effectively wrapping our code, defining a scope for our code base, we define our code blocks the same way we do in Java with curly braces. So we would open up a code block with an open brace, we'd close it with a closing brace, and every time we need to declare a variable, it has to be declared inside of a code block. Okay, where am I here? I thought, okay, thank you. Probably why I took over my my mouse controls. Okay, let's see here. Okay, so moving forward, code blocks as an additional preference, as a preface, before I talk about other control structures like branching structures and repetition structures, recall that besides defining scope, it's a way of allowing us to cluster a group of statements together so that they execute as a block, right? It should be very, very common, but recall it's still part of the a control structure definition. So that's why we open with curly braces. Now, curly braces by themselves allows us to take a group of statements and combine them together into like one complex statement, but there's no logic. It will execute in order all the statements from the topmost all the way to the bottommost. And in fact, the same experience you already have with Java, if you want to reuse a value that's stored in a variable, you have to declare that variable first before you go ahead and access it. Now, unlike in Java, and we already stated this a little bit earlier, you could potentially declare a variable and read a value before writing to it, but that could have catastrophic consequences. Java will tell you you can't do that. C will just So recall that a variable is nothing more than a label or an identifier to some memory address, right? So in a very rigid language that kind of checks for you, it's going to ensure that you have to set a value before you start accessing it. But in C, you can access the value if you want, and whatever garbage was in that memory address before you send it is still a valid binary sequence, right? It'll just grab and use it. You don't want that to happen. That the worst type of code to debug is the ones that don't throw compiler errors, because you just get like either random crashes or random like weird behavior. Anyway, with that said, moving on from our curly braces, let's go to the rest of the very conventional control structures that we'd expect. We have our if statements, which act exactly as you would expect them to. So I'm not going to spend too much time looking at those. The syntax is almost exactly the same. Also, but if statements, you might as well also say if else. So you have your selection, you have your double selection, your multi-selection, exactly as you learned in the 1583. Okay. You also have your ternary operator exactly as you would have seen it in 1583. The ternary operator is the only operator in the C language that takes three operands, a leftmost, a middle, and a rightmost, right? And it's just a condensed way of creating an if-else expression, right? So where expression one is something that resolves to be a Boolean value, right? Recall in C, our Boolean values are actually numerical values, where Z is the falsy value, and any non-zero term is the truthy value. And then your expression two would be what is effectively provided back, what is resolved back if expression to the left is true and the rightmost is resolved back if the expression is resolved false. Did many of y'all use the ternary operator in either Java 1 or Java 2? Okay, good. Okay, so moving on. Yeah. So switch statements. Are y'all familiar with switch statements from 1583? Excellent. So switch statements is another form of effectively a multi-selection statement where you actually switch off of some type of expression and you're in cases. And so it's almost, so switch statements provide almost an equality check of sorts, right? So you can't do relational checks like you could with ifs. You're a little bit more limited, and kind of like the artifice of a switch statement, now cribbing on your assembly knowledge, is going to be effectively like labels that you have inside of assembly. So you can think of it as the ability to jump into certain segments of your code. That was kind of where it came from. And so in more recent programming patterns and paradigms, it's most often avoided, right? So in a lot of introductory sequences, they'll show you switch statements, but they'll also say, hey, try to avoid those. But actually now, in even more recent shifting of patterns, they're now updating switch statements in language. In fact, you'll notice that Java has just resolved and updated their switch statements. I want to say Java 17 or Java 18, which might not be available in your textbook because I think your textbook's using Java 8. So you should probably read the actual API documentation if you want to see what modern day Java looks like. But you'll see that they're actually refactoring switch statements to be a little bit more useful, friendly, and different than how it's traditionally provided in C. Anyway, with that said, it's exactly as you would have learned it here, right? So you have your switch statement, your case, and then you have to use break statements. Otherwise, again, an artifice of how that would have worked way back as an assembly program. So you have to understand that the genesis of C came from those who are actually working with assembly, and they wanted a higher level language. And so sometimes the patterns that were decided on for C were based off of what happened prior, right? It's based off of the history of what they were comfortable with. And then as C started to get promoted and everyone saw how great it was to have these control structures like ifs and else and whiles and fors, right? Because think about how you were doing that in assembly, right? Labels and jumping up, evaluating. and jumping around. In fact, your branching logic and your repetition logic was fundamentally kind of controlled in the same way in assembly, right? It was languages like C that pioneered, let's create keywords that makes the code much more readable. And so now that dominates, right? Like C and other language that is inside the sibling of C is what established what we think of as the high level programming language that has separated from assembly. But again, sometimes we see these artifacts. Okay, let's see. Let's go to, yep, we're not going to talk that much about switch statements. Okay, let's take a look at while loops. While loops have the exact same structure as they have in Java. So I'm assuming you know how to do a while. You could do a do while as well, although while loops are typically a little bit more common. One thing you'll notice that is probably distinct between the do while inside of Java and inside of C is the format's approximately the same, but I don't think you'll notice that you need that semicolon like you typically have in Java, which makes it a little bit more confusing. It's already confusing in Java, but even more confusing in C. And then our for loop, very similar, if not exactly the same as in Java as well, where we can go ahead and put all of the loop control logic inside of the parentheses for the keyword. So you have your initializer, your loop control variable, you have your loop control, your evaluator that determines whether the loop's going to continue to run or not, and then the action that updates your loop control variable so that you can somehow fall out of the repetition. Okay, again, we have break statements. Break statements work exactly as they do in Java. They are used either in the context of switch statements or in repetition statements. They are not triggered by if statements, right? So in fact, you usually have to make a decision on whether you're going to break or not using an if statement. So for instance, if we have this while logic here with some kind of loop control expression, we have some statements, we could put if condition, and if that condition resolves to be true and we have a break, the break affects the while. Or if it was a switch statement, it would affect the switch. We also have the continue, which does exactly the same behavior as it does in Java, which means that if you have a continue statement halfway in a while loop, and if you trigger for that continue statement to actually execute, then everything underneath the continue statement will be ignored inside that body of the while loop, and then you jump to the next repetition. Okay, perfect. Does anyone have any questions over the control structures? They're pretty much the same, right? Let's move on to our complex data types. This is where we start to deviate a little bit with Java and actually C++ too. Java is more like the grandchild of C, where C++ is more like the child of C, right? And so both C++ and Java have objects, have class definitions as first-class citizens inside the language. C is not like that. C has complex data types, but we're going to be limited to the complex data types. And again, when I say complex data types, it means data types that we have and group them together to create these kind of composite forms, these composite types. Well, there's two ways that we can go ahead and create kind of our composite types in C. We have arrays, which work very similar to the way that they work in Java, although what's exposed to us is the pointers, the ways that we can reference and dereference what's held inside of an array. And very similar, conceptually at least, and again, this shouldn't be too much of a surprise because this is very similar to how your memory is managed in assembly. We also have records, which are also referenced to as structures. So we're going to look at both of those. So our structures or records, which by the way now, just to keep doing these bridges between languages, records are now a new data type that Java supports. So Java realizes, hey, maybe there is not the need to have these very full verbose classes for every particular thing. If you have something very lightweight that you don't need to define a lot of methods on, if it's just designed to group similar or some types of data together, like for instance, a point type of data, then a record is more suitable. It's much more lightweight than having to build a big class around it. So records are actually now a data type that's available in modern day Java. Is that it's going to be very similar conceptually as what you probably would consider to be like a class or like an instance or like an object of sorts, right? Where we can have a group of properties that are modeled, are different types. In this instance, in this case, we're going to do a structure that we'll call fraction. And inside our fraction structure, we're going to have two properties that are modeled using integer data types that will be a numerator and it will be a denominator, right? So I think in Java 2 or even Java 1, you do something like this with classes, right? Okay, so some important things when you define a structure, you have to use the keyword struct to go ahead, and then you have to give it some type of name. And obviously the name should be indicative of what it is you're structuring the data together to represent. Then inside of our structure, we're going to use curly braces to define a block. At the end of your structure declaration or your definition, you should put a semicolon. That's probably the #1 error that can resolve when you first start creating structures, is the lack of semicolon to say end statement, end of creation of the structure. Because what's going to happen then is it'll resolve into some error with the line of code after that. So if you see that there's a line and it looks like it's accurate, check always the line before to see if you're not missing some kind of keyword there. Okay, let's see here. The way that we can access from inside of our structure, one of our fields is with the dot operator. So again, the same kind of metaphors that you've already been kind of hammered into your head with Java, we get from C. Okay, so let's take a look at how we might copy two records of the same type using a single assignment. Now, just like in Java, you do not use the double equal sign, the equality operator, to check for equivalency between two structures, right? Because the same concept that drives Java, why that doesn't work, is the same reason why it doesn't work in structures. It'll check memory addresses effectively. Okay, but let's take a look at this sample code here. We have we're going to declare two variables, F1 and F2 on this first line of data type struct fraction. So that's how we're declaring these reference types effectively, these structure types. And then once we have declared our variables, we can access the inner values, say from the first one, so from F1, by using that particular structure's, that fraction variable's name, that label, and then using the dot operator to then access that field. And then we can do a normal assignment into it. So here on the second line, we're going to assign the value 22 into F1's numerator field. And then we're going to do the same thing to access its denominator and assign that 7. And then here, I can then simply copy the values of F1 to F2. Okay, let's take a brief look at arrays. So that's just a very quick examination into our structures. Arrays, again, are going to be very similar to what you've seen with Java. So let's take a look at the code first and foremost and see if you have any questions regarding that. On the first line of this code, we're declaring an array of data type int with a label scores. And when we go ahead and declare that, notice we're defining how many contiguous blocks of memory it's going to, or of elements it's going to be able to hold. So just like in Java, we have to define the size of our array. We don't use constructors though, right? Like C doesn't have constructors like Java has constructors in the same way. The next thing that we're going to do here is if I want to index into the first element is at the 0th index. So very familiar to what you've probably done in both assembly and in Java. And that means the last element would be whatever the size is minus 1. So in this instance, it would be 99. So again, if I wanted to create a graphical representation of what that looks like, I would have my scores array, which is effectively just an alias for where the contiguous block of memory starts at. And so inside the array, we're holding integers, right? Integers are encoded with 4 bytes in memory. Going back to here, I have the source code here. So we've created a contiguous block of memory. We reserved a contiguous block of memory that we have available to us using the scores label, but we've only assigned 2 values, right? One that was at index 0 and one that was at index 99. So if we go and then inspect representation, you'll see at index, assuming the first 4 bytes of allocated memory will have a value that would decode into 13. And then at 99, we would have a value that would decode into 42. Now, in between, we still have values. It's just garbage, right? Because we didn't do anything. So whatever those binary bits were set to before we started are still set to those values. So if we dereference them, it would result in something. But again, we don't know what it is. So you can do that, very dangerous. Another thing you have to be aware of when dealing with arrays is one of the niceties of Java, again, is that if you try to index outside of the bounds of the array, it's going to spit back a array out of bounds exception for you, right? It's not going to happen here in C, right? It's up to you, the developer, to ensure you don't do that. So if you try to index scores at index 100, it's going to be the same result as if we were trying to get one of those inner values that we hadn't assigned. We'll have active memory location. We just have no idea what's going to be there. And we don't technically have that space reserved for.
It's just like if you pull 100, it's going to just pull the next block available.
Oh, sure. Yep. And this is a real, that memory address might be allocated as a label for something else. So it might not just be that you're now storing, mutating the state of values, like the binary sequence at that memory address, but some other part of your code base might have that as a lookup that all of a sudden it's changed on it without knowing it. And this is how you can kind of get like errors that propagate in C code like weeds. It's effectively like you're kind of doing like an overflow attack at that point on yourself. Not exactly, but it's be very careful when you write C code. You have a little power, but with it, as the Spider-Man quote goes, comes a lot of responsibility. Okay, multi-dimensional arrays are still a thing, and the syntax looks very similar to what you've already seen. So for instance, here is an example on the first line on how I might declare a 2-dimensional integer array with a label of board that holds 10 elements in the outer array and 10 elements in the inner array. Now, in all actuality, it's just one contiguous blocks of memory, right? So it's not. So when you look at the memory addresses, it's the outer array. This one here, the one closest towards your label, is going to be effectively your rows, and then inside would be the rows thereafter. Yeah, so it's the leftmost and your rightmost, and then you can compute the offsets if you need to. The reason why that's worth knowing, and in this example, you'll see that, for instance, board 1.8 is going to come right before board 1.9. The reason why it's important to know this is usually one of the reasons you're using C and not a higher level language is for the explicit purposes of optimization. So knowing how your data is actually stored for access reasons can allow you to improve your code base to be as fast as possible. So like if you have to read over a collection of values, knowing how it's stored in there can get you a little bit more optimization than you would have otherwise. Okay, let's see here. We can combine these two concepts. We can have an array of structures. And so the way we could go ahead and declare an array of structures would look just like here. I would have my data type struct fraction, like what we had defined before. And then we give that a label, numbers, and we say how many different fraction structures do we want to be able to store inside this array. In this instance, we'll say 1,000. And then we can use the box notation to go ahead and index into our array to effectively access the fraction at index 0. And then we can use the dot operator to then access the field of the fraction structure at index 0. And then we can then assign those integer values there. Again, this isn't too different than probably how you're used to interfacing between kind of instances and arrays inside of Java. Okay, so this is where we're going to deviate a little bit more from Java conceptually, but we're going to lean more into probably some of your assembly background. We have this idea of pointers. So a pointer is a value which represents a reference to another value, which is sometimes called the pointer's point D. So a pointer points to a point D. You can almost think of a pointer as kind of a reference, almost a memory reference of where a value is at. And so that becomes very critically important. You're gonna see either in some documentation or in the future slides when it comes time for us to want to pass references to other parts of our code. Because by default, C passes everything by value. And again, one of the things you've learned about with Java is how it can pass things by reference by default. So it manages all this pointer stuff for you inside of Java. But here, one of our responsibilities will be that. So one of the more challenging concepts. But am I mistaken to assume that you've played around with this at least nominally in assembly? A little bit of pointer management, memory address management, to be able to dereference and access and read values. Excellent. Okay. So let's take a look at some of the syntax here. So syntactically, C is going to use the asterisk or star operator to indicate a pointer. That's how we distinguish between a pointer, a pointer to a particular value in memory versus that particular value, that particular data type. So for instance, C defines pointer types based off of the pointee, the thing that's being pointed at. So if you see something like car star, that's effectively indicating this is a pointer that's pointing to a character value. If you see something like struct fraction star, then you know, okay, that's going to be the type, a data type, which is a pointer, which is referring to a structure, but fraction. So for instance, let's move down to the actual code that we see here. If we have int star as the type, as a declaration. So these first two lines are variable declarations, but the data type is going to be a pointer to an int, and then we give whatever label makes the most sense. So here we'll call it int pointer because it's a stupid example, right? And so here we'll do the same thing. This is a car pointer that will then just label car pointer. Let's see here. Okay, one word about where the star should go. Well, I typically preference, so you can put one of two places. I kind of preference, if at all possible, for readability's sake, the bottommost. Like all these are valid. It just has to go between the label and the data type. If you're doing single line declarations, I prefer the bottommost because it's clearer to me that, hey, this is a data type, but it's not the data type value itself. It's a pointer to the data type. So I can see when you brand as part of the type, to me, that's more readable. But this is just as valid. And you will see usually with multi-line declarations where the star is prefaced in front of the actual variable name instead. But yeah, like the white space in between is completely ignored when it's compiled from its source code. So the compiler just doesn't care. It's a readability thing and a convention thing that you do for yourself and for other people who are going to have to read your code. Okay, let's talk a little bit about pointer dereferencing. So a pointer, as we said, is a value, like you can almost think of it as a memory address that's pointing to some value in memory. So we can actually use that to go to that address and access the value from there. And so that process is what's called dereferencing. Let's see here. So let's take a look at how we might do this, how we might go ahead and dereference a value that we have created a pointer for. So here we have a pointer for a struct fraction that we will call F1. So now recall F1 is a pointer to a fraction structure or a fraction record. Okay, so if we were to graphically display this, this is my F1, which is a pointer, which is pointing. And so this bold outline you see here represents the entire record, the entire instruction of what we are pointing to, of a fraction object, a fraction structure, a fraction record. Okay, so recall a fraction record has two different fields. It has a denominator field and it has a numerator field, which we're going to be inside the individual cells inside of our structure. So let's look at these expressions. When I go and just refer to F1 by itself, it now refers to the data type, which is a pointer to a fraction record. Now, if I put the star F1 in front as an expression, I'm doing a dereference action. And so what I'm going to get instead of the pointer value is the actual value in memory. Does that make sense? It can be confusing.
Like F1 is not a pointer, but it still refers to both of them.
F1 is a pointer.
Really?
Yeah, look right here, up here.
Sorry. I meant the star.
Yeah, so star F1, so by putting the star operator, it's a unary operator, by putting the star operator on a pointer variable, it acts to dereference it. So instead of returning back the memory address, it's going to that memory address and returning back that value, right? So which is going to make the third line. So here, so right here, by itself, by just the label, it's a pointer. By putting the star operator in front, now we're dereferencing the pointer and accessing what it's pointing to. Which means on this third expression, where we're doing star F1, and then in parentheses work the same way as they do in Java. So it allows us to prioritize a list of expressions inside of one statement. So here we're going to resolve the dereferencing of F1 to make this readable, and then I'm going to use the dot operator to then take that fraction record I have and access the numerator field, and the data type that's held there is an integer. Does that make sense? Again, when we start doing the labs, it's gonna, once you start doing this, it'll make a lot more sense, but it's good to kind of be aware because this is stuff that can really trip you up. Does anyone have any questions about this? Okay, wait, I see a question on here, but missed it, unfortunately. So int pointer is the pointer and int is the pointee. Yes, to answer your question, int pointer in the prior slide example was the pointer, whereas int is the pointee. Now, with that answer question, online people, do you have any questions about this particular slide? And if not, we can always come back to it. Otherwise, I'm going to move on. Okay, there's an alternate way as well to make that has a little bit more readable of a syntax for dereferencing. We can always use the arrow operator as well. So recall that F1 is a pointer. So from a pointer, instead of using the star operator in front of it, the unary operator, I can instead use the arrow operator between a pointer and a field inside of a structure. So here you're going to say, I'm going to, from the pointer, a reference, so to a reference of a fraction object, I can point to the numerator and dereference just the numerator value that way. Both of those are comparable to one another. So this line of code, F1, where I'm using the arrow operator, right? It's a dash greater than symbol to then access the numerator value. That is the same as this line here. It's just some would argue that's more readable. Okay. So now that we looked at some simple examples, let's look at even some more complex examples of how we might see pointers out in the wild. So on this first line, you're going to see where we have a pointer to a fraction record. So just like you can have multi-dimensional arrays, you can almost think of this as a multi-dimensional pointer, where you're pointing to a memory address that's going to point to some other location, like a numerator or whatnot. Why would you use a pointer to point to a pointer? That's a very good question. And so one that, at least conceptually, could be answered with, why would you want to have a list of arrays hold another list of arrays? It makes a lot more sense when we start talking about potentially building data structures that can have references to other structures that can have references, inner references to other things. So imagine if, for instance, so has anyone in 2120, have y'all looked at or talked about trees? Okay, so trees are relatively complex data types. You could start to imagine what would the process of modeling a tree data type look like using C as opposed to using Java. And then you could start seeing, oh, these are going to be the use cases of being able to have like these multi-layered ability to hold references to things. Okay, let's see here. Okay, the next example we have here is, suppose we want to go ahead and have an array of 20 fraction records. Well, we've seen what that looks like already, right? This is a repeat of what happened when we're looking at arrays. But if we want to do the same kind of thing, but hold pointers, references to fraction objects, the only difference between the two, the place we're going to put our star in this instance to declare the data type is a pointer, as opposed to a value type, is going to be on where you're declaring your data type here. So like the only distinction between the second line and the third line is the star operator to let us know we're going to point to a fraction as opposed to be holding a fraction object. Now, what's interesting about arrays, again, the concept behind that first line and this third line are the same, right? Because an array is effectively just a pointer. So if the third line makes sense to you, it's doing conceptually the same thing the first line's doing, right? Does everyone right? Because if you think about it, an array is a collection of fraction records in memory. And so what the last line is going to be is a collection of fraction pointers in memory. Okay, let's move on. Okay, so the C syntax avoids circular definition problems with a pointer structure where it needs to refer to itself. So you don't get into these circular loops. So for instance, we could create a node, going back to this idea of trees and nodes, we could define a node structure where maybe you hold some data, but one of the things about a node in, say, for instance, a linked list is that it has to also have a reference to the next node in the list. And so because of pointers, we can do this, a pointer to the next node, which gives you all the flexibility. It's not an actual node, right? It's a pointer in reference so that we can mutate that reference so we can dynamically add or remove elements inside of our linked list without breaking it.
The only thing is I don't know what to do.
Okay, just that much makes sense then? Is everyone on the same page?
I did.
Okay, so now that we talked about the star operator, let's talk about the ampersand operator. The ampersand operator is one of the ways that pointers are set to point to data. So the ampersand allows a value to provide its memory address so that a pointer can capture it and then store it. So the ampersand operator computes, it's a unary operator, just like the star operator can be applied to a variable in memory. And so suppose that I had the variable I. Was this from, did I have an example that actually used I, or we just, yeah, okay. So suppose that I have a variable I. If I put a ampersand in front, it's gonna, and suppose that I is an integer variable, then this will return the memory address of where that integer value is actually held at, and then I can save that to an integer pointer. Or let's look at the second example. Suppose that I have a fraction structure pointer, F1, like what we saw on the prior slide. And then I use the arrow operator to access the numerator field. I could then go ahead and use the ampersand operator on top of that and get back a memory address, a pointer, a address that can then be mapped to a pointer. On this second line, actually, what's that going to be a pointer to? So based off of what we know, what type of pointer will be returned here? What kind of address value that, if we want to bind a pointer to this, what's the type of pointer we would have to bind to that? What's that? Well, what's ultimately being dereferenced here? So let's look at this. So we're getting an integer value here, right? Because from F1 is a pointer to a fraction structure. And then inside there, we're then going to pull the numerator. And so here, that's going to resolve to be an integer value. And then we're going to apply the ampersand once that integer value is returned to us. So that's going to give us an address that we would have to map to an integer pointer. You could see how it can get very lost in the weeds with this, with just simple examples. Okay, why is this wrong? So the checks represent things that are valid. The X's represent things that are not right. Why can't you get the address space to 6? Six is a primitive type. It doesn't exist in memory. 6 is, so does everyone, and this is true for Java, know really the distinction between a primitive type and a reference type? Like we're talking about right now, how the reference types live in memory, right? So as my code base is running, at any time, I can access memory. I can get a pointer in memory to where those values are at. Anything that's a primitive data type doesn't consume any memory because it's literally hard-coded into the runtime environment. So things like integers or characters or everything else that is a primitive data type has a meaning that does not rely on being in memory. It has a hard-coded value. It's like if I use the symbol of 6, there's a reserved space in memory that's always 6. And you don't have access to that. That is not available. You can only use the ampersand on things that are in memory that are reference types, that are not primitive types. And that's the same reason why you can't use like equality operators and things like that as well on reference types. So that's why you can use them on primitive data type stuff, because the primitive data types, those are primitive operators that work on the primitive data types that are all built into the system. Okay, let's look a little bit more at the ampersand operator in terms of some code. So suppose that I have this function here. It has a return type void. Its name is foo. It doesn't take any parameters. So again, when we look at the functions more in detail, you're going to see it's very similar to what we call methods in Java. We're going to open and close the body of our function with curly braces. And so, okay, let's look at the actual lines of code here. So here we're going to do a declaration.
Things changes as you.
This is going to create a pointer that can hold an address that points to some integer value in memory. Here, I will hold an actual integer value. I can use the ampersand operator on I to point to set my pointer. So here I'm assigning my pointer to the value, to the address for I. And then here, now that I have a pointer to the location in memory that I holds values at, if I use star P, keep in mind star P now gives me access to the value at that address. I can then use an assignment operator to then set that value to 13. So this is all valid code, and I want you to see that I never directly set the value or assign the value of I. I grab the memory. Once I declared I now has a memory address. The value at I is garbage at that point, right? I didn't set a value, but I have an address. Once I have an address, I can bind that address. I can get that address with the ampersand operator and give it to P, which is a pointer. Then I can dereference P, set that value, and it's the same as saying I is assigned 13. Does that make sense? Okay. So when using a pointer to an object created with the ampersand, it's important to use only the pointer so long as the object exists, right? So again, keep in mind your scoping rules, because if you're running something in a function, right, and the variable is declared in that curly block, the code block, and then that code block is done, you might still have an instance where you have a dangling reference, where you're referencing something and it's been discarded. So the values might still be there, but the part of your logic is long since passed. So make sure to manage that. Make sure that whenever you're using pointers, to ensure that you never point to something that's fallen out of existence. A local variable exists only as long as the function where it's declared is still executing. Again, the rules are very similar to what you learned in Java. In the prior example that we just saw, I exists only as long as foo is executing. Therefore, any pointers which were initialized with the ampersand I are valid only so long as foo executes. Okay. Let's talk about this concept of null. So again, we learned about null inside of Java. And effectively, what you learned about null is going to be very similar to how it's used in C. It's so by default, a pointer is going to be a unsigned value. And so if it's 0, you could treat that as a null value. So 0 is a value of 0 explicitly means you're not pointing to anything. That's just how we classify a non-reference. But there's a constant value defined inside of the spec of C where null is defined as 0. So use null if you intend, instead of hard coding 0, use a null reference to set a pointer so it doesn't point to anything if you intend that, or if you want to unset a pointer, for instance. And since null effectively is the constant of 0, it represents a constant value for 0, you can also use it for any Boolean logic because it will resolve to false since it's a numerical term. And you shouldn't be able to dereference a null value, right? Like it'd be like trying to dereference a 0. Okay, let's talk about pitfalls with pointers, which I think we've already mentioned, but we'll articulate here. When using pointers, there are two indices you have to be aware of. You have to be diligent about tracking. It's the pointer itself and the thing you're pointing at. So there are three things which must be done for a pointer-pointee relationship to work effectively, right? The pointer must be declared and allocated. The pointee must be declared and allocated, and then the pointer must be initialized so it actually points to the pointee, right? What is this? Your pointer has to exist, your pointee has to exist, and you have to define at least this one-way relationship where the pointer has a reference to the pointee. If you forget any of those steps, bad things can happen. And this is just giving you, and again, this is what's called an uninitialized pointer. This is just giving you examples of how you might go ahead and do that, where you just declare a pointer, try to dereference it, like common way. So we saw earlier how this appeared to be valid so long as we also had a integer that was declared and pointing to that, and that P was pointing to that integer value. This is bad code, right? By missing that one statement, this would have been a pitfall, and one that you're just starting out in C could be hard to identify. So here on that first line, we're declaring a variable P that is an integer pointer, and then we're going to dereference that integer pointer, but we never really assigned it, right? We're going to dereference that integer pointer, and we're going to just save the value of 13 there. Well, where's it pointing to? We never bound it to anything. Okay, let's move on. Okay. So let's just take some examples. Let's look at some more examples of using pointers. So here I'm going to declare a variable to hold a pointer for an integer. Here I'm going to declare an integer I, and here I'm going to declare a structure fraction that we'll call F1. Okay, so here, these two things represent allocating pointees. This represents allocating something for a pointer. Inside this, remember that the ampersand operator means that we can go ahead and grab its address. So here we'll grab the address, a reference to where I is in memory, and we will now assign that to P. And now we can appropriately dereference P and then save into memory the value of 42 at where I has been effectively reserved for. Okay, here we can go ahead and from F1, we can go ahead and grab the numerator and then grab the address from there. And so assign this as a pointer towards the numerator on our F1 record. And then we can dereference that and assign 22. Now at this point, the value in memory where 22 is being saved at is a different location than where this 42 is at, right? Despite the fact I'm manipulating P, right? I'm dereferencing P in both instances. Since I changed what P is pointing to, I would have one value. I would have the value of 42, but now F1's numerator will have the value of 22. So you see how I can change what my pointer is pointing to, constantly dereference it, and then update the value of whatever's being pointed to. Again, it gets really fun to be able to start reading this code, right? And it's important to know what your pointers are pointing to at any given time when you're reading through your code. Again, this is one reason why Java abstracts away the concept of pointers, so that you only have to manage the idea of variables values in your mind, and you can disregard this additional constraint of remembering what the pointers are pointing to at any given time, because there's a whole level of layer on top of it. Okay, then what we can do is we can grab the memory address effectively of the denominator, assign that to a pointer, and then update that denominator to 7. So using the single pointer, we can actually assign a value to our integer and our fraction structure. Does anyone have any questions about that? Is this making sense? Okay. Let's stop with pointers for a moment. We'll reel it in, and let's talk a little bit about strings. So, again, a little bit difference between Java and C, where Java supports string as a data type natively, C does not. In fact, C treats strings as effectively character arrays, which is similar to how they're treated in assembly, right? Like, again, when we're talking about complex data types, there's only really 2 complex data types, arrays and structures. And so strings are just, even in Java, the concept of strings really falls more in line with what a array in terms of a composite type is. It's just, it's nice to have built-in functions for strings, because text is just one of the types of data we process on regularly. Like, if I had to define what are the fundamental data types that we model our logic around, that we we construct data models around, that we can then process on top of, it's numeric data, it's text data, and it's Boolean data. And usually we build our models that are composited from properties that could be any one of those 3 things, and a combination of those things. Like, for instance, if I want to model you, an individual student, you might have a name, right? You might have a GPA. You might have a status, whether you're registered or not. That right there is text, numerical, and Boolean. Yes, no, true, false. And almost anything that we are around is built because we can break complex objects and define them as a collection of properties that fall into those fundamental data types. So for that reason, we need to learn how to use strings inside of C. Okay, so C has very minimal support for character strings. We will get some functions, so there are, but let's look at the nitty-gritty on what's available to us from the get-go. Strings operate as arrays of characters. C does include a standard library, and strings are very common, as I stated before, so you have to get good at learning how to use them. But again, it shouldn't be dissimilar to what you did in assembly, right? Did y'all do much text processing in assembly? It's like taking a string of text and like maybe reversing it or something. I think that's usually the common thing that you do inside of assembly. When I took assembly, one of the projects we had to do was build a file compressor, where we had to like read through all the text, then create a compression scheme, compress it and uncompress it. That had you learn a ton of stuff that was happening for being able to do reads and how to actually like implement logics to do compression and whatnot. Okay, so a C string is just an array, as we said, of characters with the additional convention, and I think we already stated this, that the last element is the null character. And we can think of the null character as the escape 0 character. So that's how the system is able to delimit when a string is done. So the string represents string constants, such as Binky. So we have, did we talk about literal values? Is everyone familiar with the concept of literals in Java? Was that covered in your Java 1 class? It's a vocabulary term. So literal value is the actual value as it's parsed inside of whatever our environment is. And so you have certain symbols that clue in your compiler or your system that that's supposed to be a particular type of value. So I'll give you an example. If I have the number 3, I know that's an integer value because the default value for just an integer value is 3, right? If I wanted it to be I'm going to use, this works for both C and for Java. If I wanted that to be more of a long type, I would use the L after the 3, right? So the letter L is a literal value that is parsed along with that numerical data that says, hey, this 3 value should be listed. It should be set as a long type and not as an integer. It allows us to derive from the default value. Also, that's one reason why you can't start numbers with variable names, right? Because it's already parsed as a numerical thing. Then it looks after that to see what data type, if it's not the default, should it then be encoded as. Okay, if I have a period after the 3, then that's a literal value that indicates, oh, wait, this is a floating point term, right? If I use if I do a single apostrophe, the single quote, before the 3 and after the 3, that's a symbol that the symbol parses and say, oh, wait, that's a character data type. So the reason why, so if you didn't know what all that was, the very technical term is literal values. And so we have a special symbol that every literal value can be encoded as. So it's not a variable thing, right? It's the value and a way of providing context to the value that then gets stored into memory or gets accessed for an expression in some kind of way. The reason why that big, long explanation is because the double quotation, just as it's in Java, is a way of expressing a character array in a literal sense, in a literal value. So in one way, C does support strings, or at least string literals, right? Because we don't have to like create a character array and then set each character one by one. We can encode the entire sequence, the entire string of characters in between double quotations, and then C will go behind us and actually put that escape, that null character at the end. So that then lets me save it as a character array that I can then use all of my string functions on. So all this is saying here is when the compiler represents a string constant in the source code, such as Binky, what's happening is that's going to be a character array, and then it's going to insert that null character for us when it parses that text data into a string. Okay, and then the string library has lots of things that will be useful for you. Like, for instance, if you want to copy a string, you can pass in a character array. That's your destination of where you want to store the results. You can then also pass in the source array that you want to copy from. Another thing you might want to know about with strings is going to be what's the length of a string? Because strings don't know how long they are by default, right? They don't have a property value. You have to kind of track that. So if given a string, a character array, we can use this function called strlength to get back the value, and does not include the null character when it gives you that count back. Okay, why is that important? Because let's take a look at some actual code. So the following code is going to allocate a character array of 10 elements. Because remember, once we start talking about character arrays, we have to know how many characters are going to be in that array. You have to know how many letters are going to be in your string. If you don't know what the string is going to be ahead of time, usually the common thing to do when we're just talking about kind of hard coding a character array is going to be just use a big number, right? Now, that's got so many disadvantages that we're going to quickly see there's better ways to do on how we can start dynamically allocating our own memory so we can make strings whatever size we want them to be. But let's look at the easier way first. So inside of this code block, I'm going to create a character array of 10 elements that's called local string. Then I'm going to use the function that's provided to us to copy a string literal, a constant string, into that variable local string. So remember, the first parameter here is the destination. Where do we want the copy of the string to be written into? And then the second parameter here is going to be what is the source string, the source character array we want to author from. So the result of this, since we don't know ahead of time, presumably how many letters are in the word binky, this is what the resulting value is going to look like, where I have an array that can hold up to 10 1-byte characters, because characters are just 1 byte. At index 0 would be my B. At index 1, my N, my K, my Y, and then my null character. And then the rest of it is just, empty space. But it doesn't matter. It's garbage. That's garbage. The null character, when I go back to reparse and read through this string, will let me know, oh, just stop reading at that point.
Could you do the string copy and offset it? So I don't want to start at 0. I want to start at 2 for whatever reason.
Yeah, I mean, there's so local string. Yeah, there's no, so that's a good question. The question is, can you offset this right here? So we've created this character array of 10 elements. Now we haven't looked at this deeply, but I'm going to I'm going to answer this, and then we'll talk more about it in depth. We create an array. An array is simply a pointer to a contiguous block of memory starting at index 0. So I could just as readily take that reference at index 0, but I can offset it to be a pointer that starts at some other nominal address, and that would still be a valid recipient for this function call. So I could do that. Probably is going to be like the logic, though. That's going to be the thing. When you go to implement, there's lots of ways to implement logic in C, but always, always, always choose the path that's the most readable, most maintainable, and the one that is going to be the less cryptic, because that's where you're going to kind of get yourself in trouble. Try to avoid hacking things together to make it work. If you start finding yourself starting to do a lot of pointer manipulations, then say, okay, let me take a step back. Let's refactor. Okay, so the memory drawing that we saw here, and I don't want to spend too much time on this because I think we already talked about it. It just shows that the letters are only taking up the first 5 characters. Then the null character is taking the next value, and all those X's just represent space that's available to us, but we're not using for this particular string. Now, again, the pitfall here is in the code. So suppose in the code, instead we wanted to store the string, I enjoy languages which have good string support. Well, all of a sudden, because we already created a character array that was confined to 10 characters, I couldn't do that. And if I tried to do that, well, I would actually just mutate whatever comes after that character array. It wouldn't necessarily not let me do that. It's just going to mess me up tremendously. And that's why you can see text manipulation can be very arduous. Because when we start talking about overriding data in memory, and if you're not paying attention to how big your strings are, that can create problems that you don't realize are created because of your strings. And again, these kinds of considerations, one of the nice things about learning C, in my opinion, is you really start to respect some of the conventions and checks that Java introduces for you. Okay, let's go through. So here we have a copy of an example of a moderately complex for loop. that's going to reverse a string that's stored in local array. So pretty much the same thing you probably did in assembly. This is kind of what we could do inside of C. So let's take a look at this code block. On this first line, we're going to declare a character array that holds 1,000 elements that we'll call string. Then we're going to create a integer variable called len, short for length. We're going to go ahead and do string copy. We're going to take that binky value and copy that into our string array. Then we're going to go ahead and call string strlen to get the length of our string. And again, both those are using the null character to actually get the value that the string is, not the value the array is. Okay, now what we're going to do is we're going to create our loop control variables effectively. We're going to J. And then we're going to go ahead and create a character variable, which is going to hold a temporary value, because if we want to reverse a string, it's going to require swapping. And we got to pick one of the intermediary place to swap from. Now we're going to do a for loop where we'll set I to 0. We'll set J equal to the last element inside of the string array where the text ends, right? Where our string ends, not from the array itself. And then so long as I is less than J, because what we're going to do is we're going to increment I and we're going to decrement J. And you only have to get to the halfway point. If you go all the way, you'll just start swapping things back. Then you've undone all the work you went to and swapping. And then inside of our updates, we're going to increment I and we're going to decrement J. So then we're going to index into our string array. So it's a character array, so I can use box notation. I'm going to grab each element as I work myself from the leftmost side towards the right direction. And I'm going to save that into my temp variable. Then I'm going to grab, starting from the rightmost side and walking leftmost inside of that contiguous block, I'm going to dereference that value and overwrite the value at I. And since I stored temporarily the value at I inside a temp, I'll now overwrite J. And that's how we can start manipulating our string. So again, this is probably similar. You probably did something like this in Java 1 too, right? When you learned arrays, you probably learned how to manage arrays as if they were characters. So you're probably using Java in a very C-like way. Okay, and again, the convention is that whoever creates the string is responsible for making it however big they think they need it to be. But that, as a consequence, most routines that mutate your strings don't check. They'll just do what you told them to do. Like, for instance, string copy, just copy. It doesn't know if the array that you gave it is 10 elements or 10,000 elements. So again, just a source of awareness on your part when managing your strings. Again, we will look at a better way to do this. And again, two issues you want to be aware of is if it's not big enough, then you corrupt your memory. Or if it is big enough, most of the time you make it so big, you're not using like 95% of the array, right? So it's very suboptimal. It's a very suboptimal way of managing text, because either it's not big enough or it's so big that you're just wasting system resources. Better solutions here, we're talking about this, we'll mention it now, would be to dynamically allocate in your heap a amount you can allocate memory on the fly, and then when you're done with it, you can deallocate it. A little bit more management on your side, but you get a lot more optimization, a lot more performance from it. We're going to learn more about a little bit. Probably not today though, because I think I'm almost done today. I just want to see how much more until I get done through section 3. I think we're pretty close. Let me see. Yeah, I only have two more slides. I have 2 or 3 more slides. So let me just burn through those. I have my character pointer, which is another way of being able to manage my string data. If a string is nothing more than a character array, then another way of expressing a character array is to have a pointer. And then we can use the pointer operators, the star operators that we already learned about, we have to dereference and gain access. And let me see if we have. And then the last thing is going to be TypeDef. I'm not going to talk about, I kind of run out of time. Actually, let's do this. TypeDef, 2 slides. TypeDef is effectively a statement that introduces a shorthand way for defining our types. So you can start to see, if I use the TypeDef command here, my operator, I can then give it 2 operands, a type and a name. So just looking very quickly here, if I create a TypeDef where the type is struct fraction, because remember, whenever we use struct fraction, you have to use struct and then the particular name we gave that struct. So it takes 2 terms every time we want to create one variable or pointer for a struct fraction. Instead of using that, I can create a TypeDef for struct fraction that we will then use fraction. And typically when you use TypeDef, you always use uppercase letters. The rule you learned for defining classes came from typedefing. This is the genesis of that. So now, whenever I use the typedef of fraction with the uppercase F, it's a way of aliasing to mean struct fraction inside my code base. So now, when I go to declare a variable, instead of having to do struct fraction F1, I can instead just do fraction uppercase F. And then typically we will then go ahead and then just fraction after that. Excellent. So just looking at an example of how TypeDef might look in source code, here we'll do a TypeDef of a pointer to a tree node, and we'll just call it tree. And so when we go to create our structure for a tree node, we can hold our data, and then our 2 pointers that we have, we can just say tree, smaller and larger. The equivalent of this without the TypeDef is written right here. Struct tree node, then pointer to smaller, pointer to larger. We're doing the pointer in the name because we're doing 2 declarations in one go. Excellent. So TypeDef is a way of being able to start compressing some of these structures we're creating into having more meaningful single names and use uppercase. Excellent. I think we've covered a lot of ground in today's lecture. Does anyone have questions before we go ahead and dismiss? How are we feeling about C at this point? Are you guys getting eager to actually start coding in it and stop listening about it? Okay, I'm going to go ahead and try to go ahead and update Canvas with the videos from last week and today, and then I'll also try to get the intro lab primed, but not due until after we're done working through these slides. Excellent. I will see you all on Thursday then.